Welcome to Domain Driven Design Part 2. In this session, we are going to take a deeper dive into some of the more advanced concepts of Domain Driven Design or DDD. By the end of this module, you will have a solid understanding of how to design complex systems effectively using DDD principles. I will guide you through these advanced concepts today. Let's get started and explore how DDD can transform the way you approach system design. Before we dive into new material, let's quickly revisit some of the key concepts we have covered in domain-driven design. First, we distinguish between tactical and strategical DDD patterns. Tactical patterns are focused on building internal models within a specific bounded context. These patterns include aggregates, entities, and value objects, tools that help us shape the domain model. On the other hand, strategic patterns focus on the larger system and how different bounded contexts interact with each other. One of the key tools in strategic DDD is context mapping, which helps us define the relationships between these different contexts. Additionally, ubiquitous language is vital for clear communication between developers and domain experts. This ensures that everyone is speaking the same language and avoids any ambiguity in terms and concepts. The ubiquitous language serves as the bridge between technical and domain knowledge, making it easier to understand and implement the model. Now let's dig deeper into one of the most important concepts in DDD, bounded context. A bounded context is essentially a boundary around a particular part of a system that defines a specific model and language. Inside each bounded context, the domain model is consistent and isolated from the rest of the system. In practice, this means that each bounded context can have its own set of terms and definitions, and these may differ from the terms used in other contexts. This isolation helps avoid conflicts when the system becomes large and complex. For example, in an e-commerce platform, you might have distinct bounded contexts like order, inventory, and payment. Each of these contexts would have its own models, rules, and behaviors, but they must be designed in a way that keeps them independent and avoids overlap. When integrating these bounded contexts, we use techniques like domain-driven, domain events, and APIs to communicate between them. These methods ensure that each context remains isolated but still able to interact with others in a controlled manner. Now that we understand bounded contexts, we need to explore how these contexts relate to each other. This brings us to context mapping, which is the practice of defining the relationships between different bounded contexts. Context mapping is essential for understanding how the various parts of a system interact, especially when they belong to different teams or represent different areas of functionality. There are several types of relationships that can exist between bounded contexts. Let's go through a few of the most common ones. Shared kernel. This relationship involves two contexts sharing part of their model, often with close collaboration between teams. Customer-supplier. Here, one context provides services to another which depends on them. Conformist. In this case, one context must conform to the model of another, meaning it cannot evolve independently. Anti-corruption layer (ACL). This pattern is used when one context needs to interact with another without being affected by the other's model. The ACL acts as a protective layer, preventing corruption of your domain model. For example, when the order context interacts with the payment context, you might use an ACL to ensure the integrity of the ordered context model remains intact. Let's now turn our attention to aggregate roots, which are central to maintaining consistency and integrity within your domain model. An aggregate root is a main entity within an aggregate, which is a group of related objects. The key role of the aggregate root is to ensure that all interactions within the aggregate are consistent. Think of the aggregate root as the gatekeeper. It controls access to the rest of the aggregate and ensures that any changes or actions comply with the business rules. For example, in an e-commerce system, the order aggregate root ensures that any changes to the order, such as adding an item or processing a payment, are handled correctly and that the integrity of the system is maintained. Aggregates serve as consistency boundaries, meaning that only when the aggregate root is allowed to modify data within the aggregate. This guarantees that all changes are validated and follow the business logic, reducing the risk of data corruption and inconsistency. Let's take all these principles and apply them to a real world example. Suppose we are designing a bookstore system. In this system, we would define several bounded contexts like catalog, order, and payment. Each of these contexts would have its own domain model. For instance, the order context might define terms like order and item, while the payment context might have different terms for concepts like transaction and payment method. By keeping these models isolated within their bounded contexts, we avoid conflicts and maintain clarity. We also use context mapping to manage how these bounded contexts interact. In our bookstore system, the order context might depend on the payment context, but each must remain independent to allow for scalability and maintainability. To recap what we have learned so far, bounded contexts allow us to break down large systems into smaller, more manageable parts. Context mapping helps us define how these parts interact, ensuring clear boundaries and minimizing dependency. Aggregate roots maintain consistency within their domain and prevent unauthorized changes to their internal models. Before we wrap up, let's open the floor for any questions you might have. Feel free to ask about anything we have covered today, and I would be happy to provide clarification and examples. For your homework, I would like you to choose a real world system, maybe an e commerce platform, a banking system, or library system, and apply the principles we discussed today. Your task is to break the system down into bounded contexts, identify the distinct parts of the system that should be modeled separately, design aggregates within this context, and define how they will maintain consistency. Use context mapping to specify the relationships between the different contexts and how they will communicate with one another. This exercise will help you apply the theoretical knowledge in a practical scenario, and I encourage you to think deeply about how you can use these patterns to design better systems. To continue your learning on domain-driven design, I recommend the following resources: books, Domain-Driven Design, Tackling Complexity in the Heart of Software by Eric Evans is the foundational text. For more advanced insights, check out Implementing Domain-Driven Design by Wag Vernon. Courses: the Domain-Driven Design Fundamentals course on Pluralsight is a great follow-up for today's session. Tools: consider using event storming for collaborative modeling and context mapper for visualizing and designing your context maps. These tools will help you apply DDD more effectively in your projects. Thank you for attending today's session on Domain Driven System Part 2. I hope you now have a deeper understanding of advanced DDD concepts like bounded context, context mapping, and aggregate roots. These principles are powerful tools for managing complexity in large systems. If you have any more questions, don't hesitate to reach out. I look forward to seeing how you apply DDD in your own projects. Good luck with your homework, and I will see you in the next session.